Now you can start this question. So you have 40 minutes to start this coding, and then you need to explain the idea and also code it up. And if you have any doubt, just let me know. I will give you hint. And go ahead.
Okay, so this is a very famous binary search question called median of two sorted arrays. So if you know what the median is in general, it means the middle value, while the mean is the average value. And the tricky part about this is we need to do this in log n time. So we can't just use standard techniques to do this, because merging two arrays together is O of m plus m, but we want log, which is better than linear time complexity. So we're going to use binary search to do this, and I'm going to draw two examples. So let's say we have two arrays, A and B as the input. It's B is 8 elements, and let's say A is 5 elements. So what we want to do is we want to run a binary search on the smaller array first, and then use the same pivot point to find the same element in the larger array. So, but classic binary search, we know these two arrays, the input is already sorted. So that's good. And we're going to find the middle value, which is going to be 3 in this case. So what this means is initially, if you combine the length of two arrays, so 1, 2, 3, 4, 5, 6, 7, 8 plus 5 is 13. So if you were to combine these together, you would get 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 7, 8. This is length 13. This means that we have 6 elements on the left side and 6 elements on the right side, meaning this is the middle of the array. So basically, we want to partition the array into equal elements. And again, because the array is in sorted order, we don't have to actually merge the arrays together. So this is the idea. So the total length now is 13, and half is actually going to be 6. So what this means is that if we take 6 minus 3, we get 3. So the left side of the smaller array is going to be 3 elements. So we are actually going to draw this array again. BA. And what this means now is that we have our partition point. So because we found 3, we want to find 3 in the same array again. So now we have left is here and right is here. And then if we found the answer, then we'll have 4 elements, kind of like a square in the very middle of our partition, where some rules will be true. So we're going to ask, is 3 less than or equal to 4? It is. This is a perfect case scenario. Usually it doesn't work this way. This means we found our median. And if we didn't find our median, then we would keep running the binary search again and again, dividing the arrays again. But the idea is that both of the arrays, the size has to be equal. Okay, so next we're going to actually code this up, but I also think that it's important to distinguish a couple of things here, because let's say that you have an array of 1, 2, 3, 4, 5, 6, 7, 8, then another one of 1, 2, 3, 4. So in this case, again, if we run our binary search, left is here, right is here. The half is actually, the midpoint is going to be 2, not 3. That's important to understand. So again, if we do this here, then we know that find the midpoint here, then we know that here we have 3 elements, and then here we have 4 elements, so this is not equal. So in this case, the left partition isn't correct. So again, we have to update the left pointer because we don't have enough elements. We have too little elements here. We have to make it even. So, okay, so how do we do this? Well, first we have to define 2 variables for the input, and then we have to get the total length of both of them. Okay. And then as we said here, we have to get the half length. Total equals to total length divided by 2. So we're going to actually round down. That's why 13.6 is 6 and not 7.
Okay, round down. Okay.
So this is where we have to make sure we run the binary search on the small array. So if length of B, which is originally the larger array, is less than length of A, then we have to swap them so that the smaller array is on the left side. And now we can run our binary search. So let's define our dimensions. And that's what this part is right here. And then standard binary search, again, we're asking, is left less than or equal to right? Actually, no, we don't have to do this because we know we're guaranteed a valid solution. So we're going to keep running this loop until we find an answer, which we are guaranteed to find one. So we're going to find the first, we're going to divide the smaller array. So because we're using A here, which is a smaller array, and then for the larger array, we're going to use half length of total minus the half of the half minus 2 for 2 pointers. And this is where it gets a bit tricky because we have to find the smaller half of the larger array and the larger half of the smaller array on both sides of the array. So for the smaller array, we have to make sure it's in bounds because we want the 4 adjacent values. So if I is bigger than or equal to 0, then we're in bounds.
Okay.
If it's not, then we're going to define negative infinity because we're too small outside of the array.
It's out of bound. Okay.
And this is an adjacent value to the very right of it because, for example, we have 3 and 4 here. So left and right. Right is always going to be exactly one more than left. We're going to see if we're too far to the right of the array. So because we're using indices, if I plus 1 is less than length of A, then we're in bounds, else we're too far to the right, which is big, which is infinity. So we're going to do the same thing for the bigger array and almost copy and paste it here. J is bigger than or equal to 0, else equal to negative infinity. Because we have to partition the arrays, we have to make sure both arrays are in bounds. And indices are 1 less than the length always, so that's what this is for. Okay, now we have to ask the ultimate question of, have we found our answer? Have we found the perfect 4-point equilibrium? Because if A's left is less than or equals to B's right, and B's left, the bigger left, is less than or equal to A right, then we know we have an answer based on whether it's odd or even, the whole, the total. So 3, for example, is odd here. So total length modulo 2 is not equal to 0. That means we have a remainder left. That means we must have an odd length. So in that case, because of odd length, we want to return slightly bigger, the maximum of A left and B left. And if we're even, we do the opposite, return the slightly smaller partition of the 4 focal points in the middle. So turn the minimum of, if we have an even number, then 4 divided by 2 is 2. The math works out, so we can just do it regularly divided by 2. So the minimum, again, this is 2 of the 4 focal points. So A right, B right, plus the maximum of A left, B left, divided by 2. That's a perfect scenario. Okay, if this is not true for both arrays, so if A left is bigger than B right, then we're too big. So we have to move A down. So to move A down, we have to change the dimensions of the pointer because right is used to calculate the dimensions of the smaller array. So right equals to I minus 1. You can think of this as the midpoint. And in any other case, we're too small, so we're going to move the left pointer to 1 above the middle. And again, we're going to keep running this binary search until we find the result. And let's see.
Ooh, okay.
Looks like I have a bug, so.
Okay.
Okay.
It's very close now. So the problem is
maybe the minimum of A right, B right. I think that's what it might be.
Oh,
Okay.
well, ooh,
That's what it was.
okay.
Oops. Okay. Let's
Okay.
see. J plus 1 is less than length of B. Less than or equal to length of B. Huh? What's that? 1 second. Let's see. Bigger equals 0, else too small. So take the half length minus the midpoint minus 2. Right, because we divided the array. Okay. Minimum, maximum, divided by 2, yep. Okay, so one second, let me see here. This is tricky. The J should be a little bit bigger. Yeah, half length minus I minus 2, yep.
It's less than A, otherwise it's out of bound. So that's why you provide the infinity.
Yeah. So this is correct, this is correct, this is correct. So this is less than length of B, yep. Okay. Yeah, again, this can get pretty tricky, so let's go through this line by line again.
Yeah.
I still think it's maximum because odds are always less than evens. Let's run this again and see. Okay, so we're failing the odd test case.
So it should be right. Yeah, A right, B right. So yeah, I think
A right, B left, B right, A left less than equal to B right, B left less than equal to A right. Yep. A left bigger than B right. A left, B left. A right, B right. A left, B left. Yep.
So I think the 26 should be minimum A right, B right. Yeah, correct before. No problem.
Minimum of A right, B right.
Yeah.
But
the problem is
that's
what's the problem is?
Oh, was that what? Okay.
But your problem is out of bound, right? So let's see.
Yeah, 1 second. Give me a second to debug this.
Yeah, I think you almost there. Just check.
Plus 1 if J is plus 1 less than length of B, that's full infinity. Okay, let's see.
First one, length 2 equal to empty. Okay, it's 0. 1 plus 0 equal to total length 1, right? Total length 1.
Hold on. Yeah.
Oh, I know. The problem is 25. Not 25.
What?
You see? AB. You didn't change in there.
I wasn't swapping them correctly. Yeah, that's why. Okay. Yep. There we go. Okay.
Yeah. Cool. Yeah. Can't submit it. Cool.
Yep.
Yeah, just tell me the time complexity and the space complexity.
Well, the time complexity is O of m plus m because we're using binary search, so we get a logarithmic time complexity instead of a linear time complexity.
Okay.
Because we're not traversing the array the whole array every single time. We're throwing away half of it as we go.
Okay. Now about space complexity. Space
complexity should be O of n. We didn't use any extra memory. We didn't use any kind of storage mechanism.
It's not B of n. It's B of 1. Because you didn't use extra.
Oh, 1?
Yeah,
okay,
1. Okay. Yeah. Okay, good. I think, the question is very hard to explain, but you do a good job, I think. If me, I couldn't explain like you, Yeah.
I mean,
Yeah.
all
You are
right.
genius.